All right, well, in that case, let's get started. So today we're going to finish up talking about standing waves. We'll start talking about interference. That'll lead us into some more complicated interference problems next week. We'll also do an introduction to light and understanding light as a wave. Connect this back a little bit to 122 and what we understand about the electric and magnetic fields, discuss polarization, and then that'll open us up to getting into some physical properties of light. So let's start off with just talking about interference, which we introduced last week. We talked about standing waves rather. We talked about standing waves with two fixed ends. So we looked at different resonant frequencies of those, and we talked briefly about standing waves made of air. So we had these two kind of paradigms, the bottle and the straw, right? Blowing on a straw is like blowing on a container that's open on both ends, whereas a bottle was open on one end, closed on the other. And so these boundary conditions of what each end of the container looks like determines whether the standing wave has a node, which is a fixed point, or an antinode, which is a point with a large displacement over time. So for the bottle, right, one closed end, one open end, we had one node and one antinode. So that meant our fundamental wavelength was 4 times the length of the container. And that led us to some interesting ideas, which is that we can't have any even harmonics in this type of container, because if I were to double that wavelength, I'd end up with 2 nodes on each end, which violates my boundary conditions. So we go from the first to the third to the 5th harmonic for this type of container. If we're open on both ends, then we still have something similar to being closed on both ends. We still have these symmetric standing waves, but when we draw them, we can think about them with a node in the middle and antinodes on either end. So this is still, up to this point, kind of review of some of the stuff we talked about last week. There were some pole everywhere problems related to this. Finding the wavelength of the fundamental harmonic in the tube, right? The fundamental harmonic being the one where only 1/4 of the wavelength is present inside the tube. So we were looking for a case where the length of the tube was equal to 1/4 of the wavelength. And so that means we're looking at a wavelength of 72 centimeters is the fundamental for a tube of this length open at one end. So this one, the second problem was a little bit more interesting, right? Figuring out which of the wavelengths did not create a harmonic. So here, if I sketch out waves that correspond to each of these wavelengths, for example, the 72 we already know is the fundamental. So I can draw 1/4 of the wavelength fitting inside the 18 centimeter container. For 36 centimeters, right, I draw half a wavelength fitting inside the container, and that's where we immediately see a problem. So this node here showing up at the edge of the container is not going to be an acceptable solution. So this 36 centimeter wavelength is not going to create a harmonic in this type of tube. 24 and 14.4 correspond to the higher harmonics, and if we sketch them out, we can see that they meet the boundary condition of having a node on one end and an antinode on the other. So for the quantitative problem, following up on this, we can connect this to music, right? So like the note A is a frequency of 110 hertz. And so if we know the speed of sound, we can use that information to figure out the wavelength of the sound wave. So the first question asks, what is the shortest tube that I could make that could play this note? So shortest tube is my way of saying that we're going to be looking for the fundamental. If I look for tubes where this is equivalent to a higher harmonic, then the tube would need to be longer because we need to accommodate larger fractions of the wavelength. So the next longest tube I can make, for example, would include 3/4 of the wavelength, and the next one would include 5/4 of the wavelength, and so on. So the fundamental is going to be the shortest tube that I could make. So this is just another way of asking us to figure out what is the length of the tube in terms of wavelength. And that wavelength, right, I'm looking for a relationship between velocity and frequency to get wavelength. And for velocity, right, the only thing I care about is what is the speed of sound in my current conditions. And for frequency, right, we know the frequency of the note. So if I had the tube that was open on both ends, then I would be looking at a fundamental where I had two antinodes and a node fitting inside the tube. So that corresponds to half a wavelength, meaning my tube would need to be twice as long as it was in the previous case. If I used a string instead, and the string was fixed on both ends, I would get the same equation, but now I have an important difference, which is I'm going to have a different velocity, right? My velocity in the case of waves on a string is no longer the speed of sound in air. Now I care about the speed of transverse waves on this string. So I can do this problem the other way around, where I know the length of the string. So maybe I'm playing this note on a guitar string and I'm strumming a guitar string of a known length, and I can use that to find the velocity using the same equation. Okay, so that's kind of the last kind of tough problems we need to think about in terms of standing waves. The next topic we talked about this week was interference. So this is kind of our getting our feet wet in terms of interference. Coming up, we have some more interesting interference problems. So talking about things like thin films, right? Like how does an anti-glare coating work, right? How does an interferometer work, and how can we use that to make precision measurements? You know, some interesting applications of this stuff. But for this week, we're just looking at the most basic principles, which is this idea that if I'm adding up two periodic waves that have the same period and the same wavelength, then when I add those two together, I can have a situation where two crests line up with one another, where two troughs line up with one another, or I can have something in between. So one way to figure this out is to use something like a sum difference formula for a trig identity. So I'm basically adding up two cosine functions to add these two waves together. If these two waves have the same k values, right, k being 2 pi over the wavelength, and they have the same omega values, right, omega being 2 pi over the period or 2 pi times the frequency, then I can use this trig identity in terms of the sum and the difference and arrive at this expression where the sum of the two waves looks like a wave with double the amplitude, but I have this extra phase factor over here. So whether the two waves are in phase or out of phase determines the actual amplitude of the resulting wave. So the biggest case I could have, I have double the amplitude if my phase offset is 0. If my phase offset is pi, then I could be in a situation where I have no amplitude. So this phase, breaking this apart, represents something like k times the path difference minus omega times the time difference. So in the sign identity, this would be the difference term. I'd be taking the difference between these two arguments. So that means my phase difference can be from one of two things. My phase difference can be caused by one wave having to travel further than another, or it can be caused by one wave being on a time delay from the other, so leaving its source at a different time. So if we're talking about two sources and we want to say that they're emitting waves in phase, they're emitting crests at the same moment, the word we use for that is coherence. So coherence is this idea that if both sources are producing crests at the same time, then the two waves are in phase when they leave each of the two sources. So as a result, in that case, the only phase would be caused by the path difference. So I can use 2 pi over lambda times the path difference to find the phase if I'm in a coherent situation. If I'm not, then I might have a time delay that I would need to either specify or, for example, in the first practice problem where I know I'm the same distance away from each speaker, so I know that the path difference is 0. So there's two kind of key cases, right? Of course, I could be somewhere in between destructive and constructive interference, and as a result, I could find the phase angle and calculate the amplitude. The two most interesting cases are fully constructive and fully destructive interference. So if I'm totally constructive interference, that means I have a phase difference of 0, 2 pi, or 4 pi, or any other even multiple of pi. Often in some books, you'll see this just given between 0 and 2 pi. And for anything higher than 2 pi, they just divide by 2 pi, or sorry, subtract multiples of 2 pi. So, right, a phase difference that's 72 pi plus a little bit might just be given as that little bit. They might ignore any full multiple of 2 pi, since each multiple of 2 pi is just sliding an entire crest from one position to the next. So in this case, if I have no time delay, or if I have two coherent sources, then the path difference will be given by the phase over k, or the phase times lambda over 2 pi. So the phase differences that give me this purely constructive interference would be a phase difference of 0, a phase difference of a wavelength, 2 wavelengths, 3 wavelengths, and so on. So any whole integer number of wavelengths in terms of path difference would mean that my crests were still lining up with crests, and I have this constructive interference. The opposite extreme would be if I had a path difference that was some odd path integer multiple of wavelength. So if it was lambda over 2, 3 lambda over 2, 5 lambda over 2, that corresponds to a phase difference of an odd multiple of pi, so pi, 3 pi, or 5 pi, and so on. And this would be the case where I'm lining up crests of one wave with the trough of another wave, leading to the two waves canceling each other out in superposition. So if the amplitudes of the two waves are exactly the same, then in this case, I'd have no resulting wave at all. So if I have destructive interference between two light waves, then that would be, we call that a dark spot. So in the first practice problem, quantitative practice problem for interference, I say that we are equidistant between two speakers, and I'm detecting sound from two speakers, and it's almost 0, right? I'm basically getting destructive interference between these two waves. So if that's my situation, then there's no way my two speakers could be in phase, right? If they were in phase and they were emitting crests at the same time, those crests would arrive at me at the same time, and then I would be in a situation where I could add up the results of those two crests. So if I'm thinking about time delay, the smallest possible time delay that I could have would be the one where one speaker has shifted over by half a period, meaning that I've got the crest from one wave arriving at the trough of another wave. So the possible phase differences would be pi, 3 pi, or 5 pi. The smallest time delay would indicate that I'm looking for the smallest phase difference, so that would be pi. In terms of time delay, then I could figure this out in terms of the phase difference being omega times the time difference, which means that I'm looking for a time difference that's going to be half of a period, right? If one wave is emitted half a period later, then it's going to arrive with the trough when the other wave is producing a crest. So this takes us to the pole everywhere problem, where now I'm considering two coherent speakers. So when I see the word coherent, that tells me that there is no time delay. So I now have two waves where crests are leaving each source at the same time. And now I know that these two waves are interfering constructively. So if I have constructive interference, that means I'm in a situation with a phase difference of 0, 2 pi, 4 pi, or so on, which means because the time difference is 0, I only have to worry about path difference. And so the path differences I'm looking for are going to be 0, lambda, 2 lambda, 3 lambda, or some whole integer multiple of lambda. So which of these could be the wavelength of the sound? It's got to be one path difference where, or sorry, I can relate the path difference to a whole multiple of this wavelength. So the path difference here is the difference, literally the difference that the two waves have had to travel. So one wave has had to travel 6.5 meters, the other has had to travel 6 meters. So the difference would be half a meter. And as a result, I need a wavelength where some whole multiple of the wavelength is half a meter. So the only one that satisfies that here is 0.25 meters, where if I double it, I get the path difference. So my path difference in this case is 2 lambda. So one kind of fun situation to think about is what happens if I relax my requirement that I'm adding up two waves that have the same frequency and therefore the same wavelength. This leads us to a phenomenon we're going to mention but not dive too into, which is called beats. So you've heard this if you've ever listened to two music instruments tuning. When you're trying to get two instruments to play exactly the same frequency, when you start getting them close, you start hearing the sound seems like it's wobbling from loud to soft. And that's because I don't have a situation now where I constantly and consistently have constructive or destructive interference. Instead, I'm oscillating between constructive and destructive interference as the waves come in and out of phase. So I'm not consistently in phase or consistently out of phase, I'm going back and forth. So the rate at which I'm going back and forth corresponds to the difference between the two frequencies. So the closer the frequencies get together, the closer I get to having just pure constructive or destructive interference, and therefore the slower this wobble happens. So when the wobble slows down and goes away, I've tuned my two instruments right. If the wobble is speeding up, I'm getting further and further apart in terms of frequency. So this is kind of cool. You could model this out in terms of just literally multiplying out the two waves as a function of time, but there's not much else in it other than figuring out the beat frequency, so we're not going to do a ton of problems related to this phenomenon. All right, so now we have to think about light in this context. So if we want to talk about light in the context of interference, in the context of adding up two light waves and doing superposition, we need to understand how light functions as a wave. So we can, starting from Maxwell's equations, arrive at the wave equation. We're not going to run through it here. It requires a pretty solid understanding of Calc 4. In some upper division classes, we run through this. But the idea here is Maxwell's laws give us the wave equation, but they also add some extra restrictions onto what our wave can do. So our E and B waves can be waves, but they still have to obey all the rules we figured out in 122. So we still have to have, Gauss's law still has to make sense. Ampere's law still has to make sense. And so we could follow that through and arrive at some restrictions on what our E and M wave could look like. So if we start out with a periodic wave, that's kind of the easiest to visualize. We don't have to have a periodic wave. Just like with other kinds of waves, we could have pulses, we could have standing waves. Standing waves are a little extremely tricky to write down for electromagnetic fields, but we all have microwave ovens, and microwave ovens are just standing waves for light. So they obey the wave equation, so any type of wave equation solution works fine. We're going to look at periodic waves because that's the one we're most familiar with and the one we interact with the most. So the way I would think about a periodic wave, is a function of position and time, and I've got a z minus ct, where c is going to be the speed of my wave. In terms of amplitude, I'm going to write the amplitude like the amplitude of the electric wave and the amplitude of the magnetic wave. So some of the rules that we arrive at when we start applying Maxwell's equations is that the E and B fields have to vary in time and space in the same way. So that means that if the electric field goes like cosine kx minus omega t, the B field has to have exactly the same form. I can't have the electric field as sine and the B field as cosine. I can't have the electric field is a little spike and then the B field is a periodic wave. I have to have exactly the same dependence on position and time. So the same wavelength, the same period, the same phase offset. The speed of my wave I can calculate from Maxwell's equations, and it gives me 1 over the square root of mu naught times epsilon naught, which were both constants that we used last quarter. And if I plug in the numbers for those, I arrive at a speed of 3 times 10 to the 8th meters per second for light traveling in a vacuum. So I say vacuum because light will slow down in other media, and we'll have to deal with that. If you remember in 122, you may have briefly talked about how epsilon and mu can be different in other materials. So that relationship still works. If I have a material that's polarizable or magnetizable, that'll have a different mu or epsilon value, which would result in different value for speed. We'll have a simpler model to work with that coming up in terms of what we call index of refraction. The other rule is that I can't have any old amplitude of E matched with any old amplitude of B. Actually, the magnitudes of the two fields are determined. So if I know the magnitude of E, then I know the magnitude of B, and it's given by the speed of light times the magnitude of B is equal to the magnitude of E. I need to have the electric field and the magnetic field have to be perpendicular. So this one you can figure out from using, say, like Faraday's law, where a loop, if I take the electric field, add it around a loop, it has to be related to the magnetic flux. And I can do Ampere's law, something similar. So the electric field and the magnetic field must always be perpendicular, and they both have to be perpendicular to the direction of wave propagation. So that's why I drew the picture in this way. The electric field in this case is oscillating in the x direction, the magnetic field in the y direction, and the wave is traveling in the z direction. So all those three directions are perpendicular. I can't have an E or a B field pointing in the same direction as Z. It's actually Gauss's law that gives me that restriction. So because those three things are perpendicular, right, I can talk about taking a cross product of E and B, right? That'll give me a vector that points in the direction the wave is going. This is called the pointing vector. I always find this kind of funny. Pointing is literally the person's name. Someone who's named pointing came up with a vector that describes which way the field is pointing, which way the wave is pointing. It's kind of funny, but it describes which way the wave is moving, which is going to be perpendicular to the direction of the electric field and the magnetic field. Once we've got all that figured out, we can still talk about things like the wavelength and the frequency of the wave. So the wavelength and the frequency are still going to be related by this idea that the speed is going to be equal to the frequency times the wavelength, the speed being the speed of light we figured out earlier, and different wavelengths or frequencies correspond to different types of light. So what we think about as visible light has wavelengths in like the 400 to 700 nanometer sort of range. If I have shorter wavelengths, that takes me up into like ultraviolet light, X-rays, gamma rays. If I have longer wavelengths, that gets me into thinking about infrared microwaves, right? Microwaves are called that because the wavelength is around a micrometer, so microwaves, radio waves, stuff like that. So ultimately, when I put all this together, and when I'm trying to describe a wave, there's only a few things I need to figure out. I need to figure out how big, right, what the amplitude of the wave is. So that's corresponding to the brightness. I have to figure out what the wavelength of the wave is, right? So that corresponds to the color. So I can have waves that are different brightnesses, waves that are different colors. And the last thing I have to figure out is maybe the most complicated, but which way is the electric field oriented, right? If the wave is traveling in the z direction, I have to have an electric field that's pointing in a direction perpendicular to that, but that still leaves me some freedom. So our ability to determine which way the electric field is pointing is called the polarization. So if I specify the brightness, color, and polarization of a light wave, along with which way it's going, I've specified everything about this periodic light wave. So that gets us into talking about polarization. So the best way I have to visualize polarization is to sketch what the electric field is doing at different points in time. So this can be kind of tricky to start out with. The idea here is when I'm making this transverse wave, it's easy to visualize like waves on a string and what that looks like. For electric field, it's a little bit trickier because nothing is actually moving up and down in an EM wave. I'm just talking about which way the electric field is pointing. So I have an electric field pointing up or pointing down, and that's alternating over time. So I can encapsulate that by looking at a XY plane with the wave coming out at me out of the page, and E cross B, right? So I can do some right-hand rule. E cross B should always give me the direction of travel. So I know I've done this right if E cross B is going to be pointing out of the page, which is going to be the Z direction. So at different times, like corresponding to 0, a quarter period, half period, 3/4 of a period, I can draw the direction of the electric field. And so it alternates between positive X, 0, negative X, and 0. So it's what I'm representing when I sketch out that transverse wave. So technically, all I have to do is give you the electric field because the magnetic field is determined by the electric field. So if I know the wave is coming out of the page, the B field has to be oscillating in the y-axis because it has to be perpendicular to E, and it has to be pointing in the positive y at the same moment that the electric field is pointing in the positive x direction. So E cross B have to give me a vector that's out of the page. So this takes us into the more complicated example, right? So now I can think about what's going on if my electric field has a bit of a phase offset and is in the y direction. So the phase just tells me, right, when I'm at my maximum amplitude. So in this case, I'm at maximum at a quarter period and 3/4 of a period because I have this extra phase shift. Notice that B has to have the same phase shift. I can't have a B field with a different phase shift, like I said before. And so E cross B still gets me out of the page. And I know I've done all this just fine. In this case, right, I would describe this light as Y polarized. So the polarization is just telling me which way the electric field is pointing. The challenge problem I gave you was a diagonal electric field. So I have an X and a Y component. So I add those two vectors together, I get something at a 45-degree angle. And so I could describe this as an electric field polarized at an angle like 45 degrees from the x-axis. So when I talk about the polarization axis, I'm talking about what axis the electric field is oscillating on. So I also threw in two slightly more challenged ones that I didn't really ask you about, but I want to look at what happens if I take the electric field in the x direction and I add an electric field in the y direction, but now it's pi over 2 out of phase. So now I'm in a situation where the x and the y components are out of phase. This gives us kind of a really interesting special case that I wanted to talk about. It's not just because I think it's wacky. It actually is a really commonly used situation. So I'm actually going to show a little bit of a video here. So these are two components of the electric field, and this is the case that you turned in. So if I have an x and a y component at the same time, the resulting wave is going to be diagonal, right? It's going to be pointing at a 45-degree angle from the axis. If, though, one of those components is shifted, so now say the y component is shifted a quarter phase ahead, now the x and the y components are out of phase. So when I add those two vectors together, I'm going to get a resulting electric field that is going to be spinning, right? The magnitude's going to stay the same, and I'm actually going to have an electric field vector that's rotating. And this is what we refer to as a circular polarization. So the electric field is spinning around, and I can have a left or a right circular polarization, where the electric field can be spinning around in a left-handed sense or in a right-handed sense. So I mean, okay, this is kind of cool, but it's actually really important if you've ever gone and watched like a 3D movie with 3D goggles. So the way those goggles work is they work by polarization. So they can shoot two different polarizations of light at a screen. They'll bounce off the screen, get to your glasses, and one eye will only be able to see one polarization. The other would only be able to see the other polarization. If I use linear polarization, then I'm going to be in trouble if anyone in the audience ever turns their head, right? If one eye is lined up to see X polarized, one is lined up to see Y polarized, then I have to keep my head perfectly still throughout the whole thing, and that's not going to work. So instead what they do is they use the two circular polarizations, left and right hand circular polarized, to correspond to the left and right goggles of, or eyes of your 3D goggles. The last bit, talking about polarization, I'll come back to those other questions in a second. I can make devices that are called polarizers. So the idea of a polarizer is it only allows an electric field to pass through if it's oriented in the right direction. And I can kind of think about that like setting up like little strips of conductor, right? I know like conductors don't allow there to be an electric field inside. So if I set up some vertical lines, then only the electric field that's pointing perpendicular to those lines will be allowed to pass through. So if I have light coming from, say, like a light bulb, it's not any particular polarization. It's kind of like a random average of all the different polarizations. If I pass it through a polarizer, now the stuff that comes out is polarized in the same direction as the polarizer. The amplitude, or the intensity rather, is also going to drop to half. And that's easy to just remember, but where it actually comes from is taking the integral of cosine squared theta, right, over all the different values of theta. So I have all these different orientations that I could have for the polarizer, and I'm integrating all the different averages, and that's going to give me 1/2. So we don't have to be able to do that. We just have to get that a single polarizer. If I start with unpolarized light, it gives me 1/2 the intensity out. If I run already polarized light through a polarizer, the amount that comes through goes like cosine squared of theta. So the larger the polarizer angle from the axis of polarization, the less of the wave gets through. And the resulting wave that comes through is going to be oriented along the direction of the new polarizer. All right, so let's go back to some of these electric field concept questions. So in one case, I've got these three waves, right? Case 1, case 2, case 3, and I ask about these three statements. So let's look at these in order. So one is that case 2 is brighter than case 1. So brightness, and the way we see brightness, has to do with the amplitude of the wave. So case 2 does have a larger amplitude than case 1, so that makes sense. Case 2 is brighter. In B, case 2 is moving in the opposite direction. So this is where that pointing vector comes in. And if I take the cross product of E and B, it'll tell me which way the wave is moving. So in case 1 and case 3, I'm going to get a velocity that's pointing to the left. And in case 2, I'm going to get a velocity that's pointing to the right. So yeah, that makes sense. In case 2, the wave is moving in the opposite direction. Statement C, case 1 and 2 are the same color. Color, right, is what we think about in terms of wavelength, and it does look to me like case 1 and case 2 have the same wavelength, which would be the same color. That makes sense. So that just leaves D. So case 1 is green light, and case 3 is violet light. So violet light, I would expect to be a higher frequency and therefore a shorter wavelength. So case 3 actually looks to me like it has a longer wavelength than case 1. So D is going to be our answer here. Okay, this one is one of my favorites. So this kind of gets to what we're actually saying when we say we have an electric field pointing in the X, Y, or Z direction. That means literally that I have an electric field, meaning that if I have charges that are free to move, they will experience a force in that direction. So if I have just a wire that's not hooked up in any sort of circuit, and I line it up with the electric field, so in this case, the electric field is in the Z-axis. So if I line up this wire along the Z-axis, there will be an alternating electric field parallel to the wire, which would result in a force on charges in the wire that would move charges up or down inside the wire. So I could get a light bulb to light up by wiggling charges up and down on this wire. And this, again, is not actually just super abstract. This is exactly how antennas work when we transmit signals and pick them up with antennas. So the electric field oscillates charges in the antenna with a certain frequency, and we can build circuits that detect those frequencies and use those to receive signals. Okay, so that's everything I feel like I need to say about these topics right now. If you, at this point, have any questions, I'd be happy to take them.